Yeah, wonderful to be here with everybody. I'm having a wonderful time at your conference. Again, I'm Bruce Momjian. I work for EDB. And we are going to go over the most complicated talk I have on my website, okay? We have 62 talks. This is the most complicated one. We have 40 minutes to do it. This is going to be interesting. If you'd like to look at the slides, they're basically right there at that URL. The QR code obviously matches. How many people were at Ben Dalton's concurrency talk earlier today? Okay, 1, 2, 3. It's not every day I have an opportunity for somebody to basically set me up for my talk, but effectively that's what he did. He talked about different isolation levels. He talked about concurrency. He talked about why you'd want one or the other, and I thought that was a great sort of setup. This talk is going to be a deep dive into how Postgres implements multi-version concurrency control. That might not mean a lot to you, that term, but when we finally do talk about it, I think it will make sense. This is a talk that it took me a long time to understand this concept, so do not be surprised if you also have confusion. I'll try and take questions as I go, but again, I have 40 minutes, so I'm going to just do my best to crunch everything in. People who are coming in, probably this area right here is where you want to go. There's a bunch of seats right over here. Okay? All right, great. So I always like to start my talk a little interesting. These are a number of actors who you may recognize one or two of them. But you may not certainly recognize all of them. But what's interesting is that they are actually the Star Wars cast. The big guy is Chewbacca there. Princess Leia you may recognize. R2-D2 probably not, right? But what's interesting is once you see it, then you look at the film differently. You look at the actors differently because you realize that Chewbacca was a guy in a suit and R2-D2 was a little guy in a machine, okay? And the reason I like this slide is because, again, MVCC, you use it all the time, but if you understand how it works, it appears quite a bit different. Again, the majority of open seats are right here, folks. If you're coming in late, they're pretty much right here, okay? Why is MVCC important? Why is it worth understanding? There's probably 3 major reasons. One, by understanding how it works, you can predict concurrency behavior. So concurrency behavior would be, how do you predict how a system would work? One of the great things about a multi-version control system like Postgres is you can have multiple people reading and writing at the same time, and there's minimal impact from those people reading and writing at the same time. Secondly, there are some performance impacts that I'll talk about, and also some storage space issues regarding MVCC. But again, this is a really complicated topic, but if we get, I think by the time this is over, you'll understand what I'm talking about. Okay, so we're going to introduce MVCC. We're going to talk about the implementation, and then finally talk about more practical things, the cleanup and the requirements and the behavior of that cleanup for MVCC. So what is MVCC? It stands for multi-version concurrency control. It allows high concurrency even during significant read-write activity. One of the great things about MVCC is the sort of slogan that readers don't block writers and writers never block readers. And I think that's a very powerful capability. Those of you who have used locking implementations, which Postgres is not, but locking relational systems that use locking have a lot of downsides compared to MVCC. So again, that non-blocking behavior is super important. Most relational systems do support MVCC. Oracle was one of the early ones. MySQL with InnoDB, Informix, Firebird, and oddly, MSSQL supports both, either one, which is really kind of interesting. And Ben did talk about that this morning, the concept that Microsoft SQL has MVCC and locking implementations. And you can actually choose the one you want, which is pretty amazing, frankly. So this slide is going to be the sort of cornerstone for what we're going to be talking about in the next 10 minutes. And it's basically a blow up of three different rows, okay? The top row is an insert, the middle row is a delete, and the bottom row is an update, okay? And again, this is very abstract. It's not really something you would see, but I'm going to show you later that you can actually look inside. You can actually see the MVCC implementation of Postgres. But again, this is abstracted out. So every one of these versions, there's 3 rows, but there's technically 4 tuples or four kind of rows in this, because you might notice the delete is made of 2. And I'm going to explain why that's important. But let's start with the insert. So the insert, and in fact, all of these rows have invisible columns. We're going to call the first invisible column the creation column for the row. And the second one we'll call the expire column for the row. Okay? And you don't see these normally, but I'll show them to you later. So the first one, you can notice, it's telling me that row was created by transaction number 40, okay? And you can also notice that there's no expire on that row, okay? The delete, the second one, you notice that it's created also by transaction 40, okay? But it's actually been deleted or expired by transaction 47, okay? And perhaps the most unusual case is the update, created by 64, expired by 78, but a new version of that row has been created also by transaction 78 and has no expire location, okay? And the bottom row is really the fundamental aspect of MVCC. In locking implementations of relational systems, you usually have one version of a row, okay? But in MVCC, you literally have multiple versions of a row, particularly for an update. So what happens in the update case is you have an old version of the row, which is marked as expired, and then the update creates a new version of the row, which does not have an expire. Okay? Why is this important? You remember this slide where I said that readers never block writers and writers never block readers. How can we do that as a relational system? Because people are writing and reading all the time. The way we do it is this. So what happens in a relational system is that when you do an update, the old row remains so that readers can see a consistent view of that row, okay? And the new version is created, obviously, for future transactions, okay? So you actually, the update case is really what makes it multi-version. And obviously, this allows us to do inserts. We can do all sorts of modifications to the database while not blocking people who are reading the database. Okay? Does that make sense to everybody? Great. Any questions?
Is this the thing that enables isolation levels?
Is this, yes. So the question is this a thing that labels isolation levels? I will actually talk about that because isolation levels is actually key to this issue. Okay, great. Other questions? Yes?
So in the update case, the
yeah.
CR is 64, right?
Yeah.
Isn't it should be 40?
Wait, no, this is just a stupid example. Yeah, I just picked something. It could be 40, it could be something else. Yeah, sir.
So what will be the case in case of rollback?
Okay, the case of rollback, I'll talk about that later. Okay? So it sounds like all the questions are going to be future. Let's just roll. Let's roll forward, right? Yeah. All right. Good. Look at that. All right. This is a key aspect of this gentleman's question about isolation levels. there is, and Ben did talk about this concept in his talk, although he didn't have any slides that not in detail as I do. But we're going to now roll into some really interesting slides. Just be ready, okay? So there is a concept in Postgres, and frankly all of the MVCC implementations, called a snapshot. And a snapshot, in my understanding, is a predetermined view of how I should view the database, okay? So the really weird part about MVCC, and the reason it's confusing, is that normally if you open a box and there's 3 things inside, you assume that everybody else who's looking at the box would also see 3 things at the same time. Because it's a box, there's one box, we're going to open it, there's 5 people, they all look in the box, there's 3 things in there, we can all agree on that. That is not true of MVCC. As different people approach the box at different times, because we're adding and removing rows all the time, different people see different number of things in the box, all right? And that is the weird part of MVCC. It works fantastic, but I'm going to still call it weird, okay? Because that's not the way we normally view the world. We view the world as a static thing. There's either 3 things in the box or there are 4 things in the box. But because we're allowing people to look in the box at different times, and we're allowing people to change the number of things in the box while other people are still looking in the box, okay? If somebody sees 3 things in the box, we assume they're going to continue to see 3 things in the box, even if somebody later adds or removes things from the box. That's what a snapshot does. So what the snapshot does is it controls which rows are visible to a statement. And a snapshot is recorded at the start of every SQL statement in read committed mode, okay? And only at transaction start in repeatable read and serializable mode. What does that mean? What that means is that if you have a transaction block and you've got 10 statements, if you're repeatable read mode, you get a new snapshot every statement. Okay, Ben did cover this in general, okay? Every new statement sees new committed data. If you run the same transaction block in read committed mode, because we take only one snapshot at the beginning, you see a consistent view of that database throughout the entire snapshot, through all of the queries. And there's a lot of value, particularly for reporting, to have the ability to do serializable repeatable read capabilities. Okay. So the beautiful thing is I'm actually showing you what the difference is internally between repeatable read and serializable. And repeatable read and read committed. The 2 things we record internally when we take a snapshot, and again, every transaction may have a different snapshot, right? They may see different number of things in the box, okay? We record the highest numbered committed transaction, and we record all of the transactions that are currently running, because a currently running transaction is not committed, and therefore we assume it's not active for us. We can't see the effects of a transaction that was running when we took our snapshot, okay? So using the snapshot information, Post can determine if a transaction should or should not, if a transactions should be visible to an executing statement, and that's really the question, all right? So, remember I showed you those pink squares before? Now we're going to roll through, and let's see if we can predict, we can figure out why some of these rows are visible and some of them aren't. All right? It's kind of out there, but so take a look at the right-hand side. What's our snapshot? What is our snapshot? Our snapshot says highest number committed transaction when we took our snapshot was 100. Okay? Therefore, everything 100 and greater is not, we can't see. We can't see the effects of everything over 100. And also 25, 50, and 75 were running at the time we started. So those also are not visible to us. So first row, created by transaction 30. Is that less than 100? Yes. Is it one of the running transactions? No. Therefore, that create is valid. And there's no expire, so we can see that row. Next one, created by transaction 50. It's less than 100, but it's one of the running transactions, so that row we can't see that row. Okay? Third one, created by 110, too high. That was created in a future transaction, started after us, we can't see it. That's why that one's invisible. Bottom. The bottoms are trickier because it has creation and expire. So you got to figure out which, the creation has to be valid and the expire has to be invalid for us to see it, right? So first one, we know this one, 30, we know that's visible. Expire of 80, that means the expire is, both of them are valid. The creation's valid, but the expire is valid. So we can't see that row, okay? Second one, creation 30, expire of 75, we can see that row because it's a running transaction, okay? And then finally, creation 30, expire 110, again, that's visible because the creation's valid, but we can't see the expire, okay? Internally, the creation is called Xmin and the expire is called Xmax, and I'll show you that later on, okay? Any questions? Wow, if we got through that slide, I'm feeling pretty good. Because this is, yeah, so we're gonna turn it up some more, okay? We're not done yet. Somebody want to guess what this is? What this is it shows you visually transactions that are visible to my snapshot in green and transactions that are invisible to my snapshot, they're in red, okay? So the reason for that, for example, the first one is invisible because it didn't commit at the time I took my snapshot, right? Because it was running. It's one of those running transactions, right? The second one committed before my transaction starts. That one's green. The third one also committed after my transaction snapshot I took. The fourth one, the same thing. And the fifth one, again, that worked. And the bottom one, that's like way in the future. That started after my transaction. It's not even like close to being valid. All right? Yes? So this last one you're asking about? Okay, so the creation is valid. The expire is not valid because it's in the future. This 110 is higher than this highest number committed transaction. So the creation is valid, the expire is not valid, therefore it's visible. I would just walk around the house thinking like, what? Like, huh, right? It takes a long time to think this way. I would almost argue that you're probably going to need to go back to my website and watch the video again or 3 times to kind of get it, because you're right, it is really, it's just not like the real world. Whoever thought of this was amazing, you know. The researchers from, yes. Yes, sir? What's the, I'm sorry? I'm sorry, I didn't understand that. We got to move on. Okay. I'm not, honestly, I'm going to go with this. Okay, and I'm going to stick on this thing. This guy, Mike Olson, 1993, he said, the tests in this routine are correct, and if you think they're not, you're wrong. And you should think about it again, and I know it's happened to me, so I'm just going to sit on that, all right? I'm sorry, but I've gotten confused so many times, and this slide deck has been unchanged for so long that if I'm wrong, please email me and we'll figure it out, all right? But this is, I know Mike Olson. I actually talked to him a couple weeks ago. I mean, this is how many years ago your brain starts to go crazy on this. And I just love this. And again, this is from a specific C comment from the Berkeley days, long before I even started. It's craziness sometimes. This is Berkeley DB and Cloudera, Mike Olson. Yes, great question. Yes, that's the Mike Olson guy. He has somebody who wanted to help us, and in fact, all he is known as is MAO in our code. We don't even get his name. We just say MAO, and then we figured out that was him. And when he was at university, he worked on Postgres. That was kind of funny. It's kind of funny I had that lined up. OK, so let's talk about implementation. How do we implement this inside of Postgres? We're actually going to install some extensions, and we're going to look inside to actually see this thing. Page inspect and PG free space map I'm going to install. So I create a table called MVCC demo. I load page inspect. I load free space map, and I create a little function here. Okay. Again, if you want to run this presentation, go to this URL right here. Okay, right? If you download the slides and you click on the blue, it'll load a SQL file. You can literally run this in PSQL, and it will run the entire presentation on your screen and just fly by. Okay, so again, if you're thinking I'm making this up, you can actually try it. The numbers will be a little different, but it'll look almost the same. Okay, great. Okay, so do you remember I said there's a creation and expire? And remember I told you it's called Xmin and Xmax? That's actually what I'm seeing here. Here's the bizarre part. I do an insert. That is my creation in red, and that's my expire in black. Remember? We had the numbers. One was, right? And that's exactly what we expect to see. Okay? This is the first box here, right? It has a creation. It has no expire for an insert only. Okay. So now I'm going to delete the table again. I'm going to insert a row. Again, we get our 5411 again. And I'm going to begin a transaction very similar to what this gentleman did. And I'm going to delete from the row, but I'm not going to commit yet. All right? Whoa. There it is. Right? That is our expire for the delete. Okay? And in fact, it's telling me I'm 5421. And you can see I've taken the row I created here, and I've changed that 0 to 5412. Okay? And once I commit it, the row goes away. And now every new snapshot will see my delete. Right? Until I commit, they don't see it. And that's exactly what this middle one is here. Now we're going to do the update, which is kind of the most complicated one. Okay? So here we have insert a 1, and you can see my row right here, 5413, right? We're looking good here. No expire. We begin, and we change the 1 to a 2. All right? There's my 1. There's my 2. Both rows are in the database. The top one is my current transaction can see my own update, because you see your own changes within your own transaction block. But because I haven't committed yet, another PSQL session that I indented here still sees the 1, but it sees my delete, but my delete number is a running transaction in its snapshot, and therefore it ignores the delete. Did everyone get that? Okay. I'll say it again. I see my own change, obviously, the 2. But what I did, I started another PSQL session. Before I committed, that new PSQL session took a snapshot. It figured the current transaction counter, and it recorded all of the running transactions. And it knew to ignore anything from any of the running transactions. One of those running transactions in that snapshot is 5414. So when I do a select on that table, I still see the 1, but I also can see the Xmax, the expire, but I'm ignoring that because my snapshot tells me to ignore that, anything that happened with 5414. Okay? And then once I commit, this is actually what we have here. We're marking the delete, and then we're creating a new one. Okay, and then obviously once I commit, then all new snapshots will see the 2. They won't see the 1 anymore, and we'll clean up the 1 later on. And I'll explain how we do the cleanup as we go. Any questions? Yeah, no, oh, yes.
And how MVCC store component update same row?
How does MVCC, I'm sorry?
Concurrent update same row. If I start to transaction concurrent.
So how does it concurrently update the same row? It would continue creating more and more versions of the same row. So if you had people continually updating, we might create 5 versions of that row. All would have different expires. And they would just, but what actually is kind of interesting, and maybe what you're asking, is when you update a row, you always see the most current version. You actually break out of your snapshot when you go to update, and we always update the most current version in the chain for that row. Okay, even if it wouldn't technically be visible by our snapshot. Pavan, who spoke yesterday at the keynote, he was one of the people who sort of, if you want really details, he would be able to explain a lot of that to you, because there's a whole cleanup stuff that he implemented related to this. Okay, it's actually really interesting. And Ben Dalton did talk a little bit about the fact that read committed kind of, for reads it's fine, but for writes it kind of breaks out of this read committed snapshot concept. Okay, I'm not going to go into that, but that's probably what you're getting at. Okay, what about an aborted transaction? I think somebody, I don't remember who asked about that, but let's go through it. We do our insert, we put a 1 in, we begin our work, we do a delete, we roll back. Here we have the old row again. It has an expire, but this is another case where, because we rolled it back, we actually have a big system table that records all of the aborts. And when you look at 5416, it looks up in this big system table and it says, that is a transaction I should honor, but it didn't commit, and therefore I'm going to skip it. The actual system file is called PGConf. You'll see it in the data directory. It has 2 bits for every transaction. Okay, so every byte can record 4 XIDs, and effectively the creation is you got the creation ID and then the expire ID, and that's what these 2 numbers are, the XMIN and NIXMAX, and it's basically offset so you can, and there's the legend of what they look like. Okay, so that's how an abort is handled. We actually don't go back and clean up the rows in an abort. All we have to do is mark the transaction as aborted, and every future transaction will know that that's aborted. So aborts of transactions are super fast because all we have to do is set a bit, right? And just keep going. Really interesting implementation, I think. Okay. We also use the XMAX field for row locks. So for example, when I do a select for update right here, you can actually see that we actually put a field on there, but we also set like an internal bit on the row that explains that the XMAX is really not an XMAX, it's really a row lock. Again, you're probably not going to deal with this so much, but if you're doing for update, this is how we do for update. We literally put transaction IDs on the row, but we mark it special so it's not considered to be an expire, it's like a row lock, okay? And then you can sleep on that row lock waiting for it to commit, and then you can continue. If you're doing concurrent for updates, this is how we would implement that. Okay. Multi-statement transactions, again, it follows the same rules. Here's an example. I'm inserting 1, 2, and 3. Okay. When I go to look at my table, you can see there's actually the 1, 2, and 3 here on the left, on the right, and then you see what we call the CMIN. The CMIN is a sort of counter that we use for multi-statement transaction blocks. So you can see we did 3 and then we commit. That's how that works. Here's another example of a delete. We have this. We actually create a cursor. We delete, and you can see that the XMAX has marked all of these to be deleted. Okay, again, same process. You can update the CMIN. Again, if you're updating rows within a transaction block, you can actually see I've converted 1, 2, 3 to 10, 20, 30. And you can see it's CMIN number 3, which has done that. But if we fetch from the cursor, we can see the old values from our data. I know it's kind of crazy, but I'm showing you an example where you did an update, but you can also, using a cursor, see the old versions, which is kind of crazy, but it works, okay? If you modify rows from different transactions, again, we inserted 1, we open a transaction, we do 2, 3, and 4. You can see the 1 was created by 5424, 2, 3, 4 were created with 5425, right? So this is a case where I'm showing you a table that has rows from multiple creation transactions, right? And again, if we modify again, you can see that the exact thing has happened, okay? There's something called combo command ID. I'm not going to go into it. I don't think I have enough sufficient time if we want to talk about cleanup, but it effectively is an ability to internally combine if you create and delete a row in the same transaction block. In multiple statements, we have a special something called a combo command ID that allows us to do this. And again, I'm showing you sort of what that looks like. And again, this is using the internals page inspect. I can show you the old versions of the row here, the first 3, and then the new versions of the row, and kind of how that works. Again, this is very detailed, not really relevant all the time. You just need to realize that we do have facilities to handle this. Okay. So in summary, the xmin is the creation, the xmax is the expire, and then we have also something called cmin, cmax, which are designed to handle rows that are created and deleted in the same transaction block, but by multiple statements in that transaction block, because that actually becomes important. Okay. Any questions? Yes.
Creating a snapshot, say in the morning one user has come, it has an open transaction, they committed. After that, the whole day, any different users have come. The first transaction is still open. How big the snapshot can sustain?
So the question is, if you open a snapshot in the morning and you leave it open all day, and other transactions are coming in, because you have an open transaction, we will not do any cleanup in the database you're in. We might do another database, but the database you're in, we will not do any cleanup because you might need to see versions of the row that you started your transaction block in, right? So again, having an open connection is not an issue, but if you have an open I guess if you have open repeatable read transaction block, we would not do the cleanup. If you have an open read committed one, we will, because we don't guarantee we're going to give you a consistent view. Okay? In most cases, we're only going to, in most cases, people are going to use repeatable read, and we only have to keep we don't have to keep the rows for the duration of your statement. So if you have a big query and it takes an hour, we won't do any cleanup during that, while that statement's running. But because you're in because you're in read committed mode, as soon as you finish that statement, even if you're in a block, your snapshot goes away. So then we can start cleanup again. Okay? I'm going to have to keep going. I'm sorry. In fact, I'm going to be talking about cleanup right now, so this might clear it up. So we have to do cleanup. Now, even if we didn't have MVCC, we still have to clean up deleted rows and aborted transaction rows. So we still have cleanup, but we got more cleanup with MVCC because we got to clean up all the updates, okay, particularly. And we also have to clean up the delay, we have to delay the cleanup of deleted rows, again, if we have open transactions, okay? So again, we have a cleanup capability in Postgres. It's a little harder because we have MVCC, but we'd still need one even if we didn't, basically. There's 2 types of cleanup. There is what we call an on-demand cleanup, and that happens as Postgres is accessing the table, as it's reading rows, it will do dynamic cleanup and removal of rows that it knows are not visible to anybody. And we also have an auto vacuum or a vacuum process that can be run in off hours to also do that cleanup in bulk. Okay? So both of them are actually automatic, so you don't have to do anything about it. The on-demand one happens as you're updating and reading. Even a select will do a cleanup, frankly. but the bulk process will happen typically by auto vacuum. So again, what can we do? We can remove the data row, we can remove something called item pointers, and we can remove something called index entries. There's actually 3 cleanups that we potentially had to do here. So this is what a page looks like in Postgres. We have a header at the top, and we have item pointers. And the item pointers point to data, in this case tuples or rows, and they are at the back of the table and they grow forward. So the item pointers grow from the top to the bottom, the rows grow from the bottom to the top. When the 2 meet, the page is full. We go for a new page, okay? So here's the way the structure is. The indexes point to the item pointers point to the data rows, okay? And there's some advantages to this sort of layout. So for example, if we have some rows, let's suppose row 2 and row 1 are invisible, they can't be seen by any transaction, right? Because your long query is finished, okay? So let's suppose we're doing a select and we're like, row 2 and row 1, they can't be seen by anybody, so we're just going to mark the item pointers as dead, and we'll just get rid of the space for 2 and 1. Okay? But the indexes still point to there, so we can't get rid of the item pointers. They have to stick around. All right? And then later, when we perform vacuum, we can remove the item pointers as well, because we're going to clean up the index and remove the index pointers. So that's why the on-demand cleanup and the vacuum kind of work together to keep your system clean from MVCC. Okay? So let's take a look at what this looks like. We're going to actually fill a table to 3% full. We're going to insert a row, and effectively here we have, this is an internal, we're seeing internally what's happening in Postgres. You can see I have a row right here, 221, and then 222, and you can see that 221 is expired, all right, because I just know that that's a dead row. Nobody can see it, okay? So if I do an insert and a delete, and I do a select again, notice 221 has been marked as dead. So it's that same case where I've actually marked the item pointers here as dead. And that's exactly what we're seeing here is dead. And again, if I do a select again, it actually marks more of them as dead. Here we only have one dead one. 222 and 223 are still active, but you see there's an expire on 222. Okay, and when I do a select again, now both of them are marked as dead. So that's my on-demand cleanup right there. It's basically cleaning up exactly as it's running. Here's a select statement, literally cleaning up the database. And again, it marks those as dead. We can then run vacuum or auto vacuum, depending. And once I do that, you can see instead of marking them as dead, we're now marked as unused. Okay? And that's what this is. Now the item pointers are now empty, and we could reuse them. Before, remember, the item pointers were dead, and they were taking a small amount of space on the page. Very small, but it's there, and that's why we have the vacuum to run. Okay? The free space map actually tells us where to put new rows. So here we look at the free space map is empty. And now if I insert a row, you can see the free space map is pretty full. If I then run an insert and then I run vacuum again, you can see it actually has more free space because we kind of cleaned up some of the data. I know it's this kind of detailed, but free space map is just used to find empty space in the system. Okay. Vacuum removes stuff at the end of the page. So for example, if I delete all the rows, vacuum will actually shrink the table to 0. So if you have empty pages at the end of your table, the vacuum process knows to just remove everything. Or if let's suppose you have 5 empty pages at the end of your table, it'll just remove the last 5 empty pages and shrink it down. Okay. We also have optimization for single page cleanup. This is what Pavan did actually as part of Postgres. This thing called hot updates. As you can see right here, the description. I'm not going to go into it because I don't have a whole lot of time. But the concept is that as you go and delete and have multiple copies of the row, if you do not modify the index while you're doing the updates, we can literally piggyback and keep the same index entries and basically continue to expire and add new rows as old update rows are no longer visible. And we can do this efficiently because the index continues to be kind of point to new rows. You see how the index is actually getting to hop between them. And this was incredibly powerful. So it allows very high update workloads to not consume excessive space because it can actually remove the old updates very quickly. It doesn't need to create index entries for them. This was revolutionary, probably done 12 years ago. Okay, and then finally, you eventually do, a cleanup, and eventually there's a redirect right there. Again, here's the redirect. You can notice this was 222. Now it's redirected to 223. And finally, you basically get a cleanup where you run vacuum, and now the whole thing is cleaned up. Okay. So again, if you run vacuum itself, vacuum is a more powerful cleanup, and it will automatically wipe out all of the stuff. So again, updating, if you modify an index column, we can't do this anymore. So that's actually something to keep in mind. If you're indexing and you update an index column, we can't do this optimization anymore. Okay, and I'm just going to kind of show you what happens is you accumulate more and more dead rows because we can't do the hot update in that case. Okay, and this is my final slide, effectively trying to summarize single page vacuum when that happens, single page cleanup when that happens, and then vacuum when that happens. Unfortunately, I do not have any more time. I was supposed to finish at 2:40, and that's exactly what it is. I will be here to answer your questions. You have about 5 minutes to get to the next session. I hope I answered enough questions so it was worthwhile. And thank you very much.
Thank you, Bruce. We can take a couple of questions if you want.
So this Xmin and Xmax, these are physically present within the tuple in the page.
The Xmin and Xmax are literally in the table, yes. This query that I'm showing you, you see how I'm saying select Xmin, Xmax right up here?
Right.
This is literally real queries. You don't, if you do select star, you don't see it, but if you ask for Xmin, it'll show it to you.
Understood. Yeah. Then second question, does Xmin and Xmax, are these present within the index also, within the structure?
They're not in the index, no.
Then does that mean while accessing index, it
yes.
accesses the table Xmin and Xmax?
The index has to go check the table, but then sometimes we'll go backward and update the index to say if it's all visible or not. So we have a little marker. If we're going to the index and then we go to the heap, we find that the row is not visible to anybody, we'll mark the index and so that future transactions don't even bother with it.
So this happens within the select itself?
Yeah, it won't bother, yeah.
Okay.
Select will do this, absolutely, yeah.
Okay.
Okay.
We're good? We're done?
Yeah.
So I have questions related to, so I have an index with respect to one table, but I do multiple update on that. So do I get multiple entry in the particular index, but that multiple updates?
Yes. So if you're updating an index column, then you're going to get multiple index entries for every update that you do, and only vacuum can clean those up. Yeah, that's a great point. That's what I was trying to highlight back here. That you can't. You see, where is it? Yeah, you can't clean up the index with single page. You have to do the vacuum. Yeah.
Okay. Thank you. Thank you very much, Bruce.
Thank you, everybody. Appreciate it.